In this video, I'll talk about the parallel combination of resistors. So here we have three resistors R1, R2 and R3, and these resistors are connected in parallel configurations. So when I say parallel configuration, that means the potential difference across this one is exactly the same. Okay, but the current, as the current passes, the current will be divided because it does have now three different paths. So parallel means the different paths now. So the current will be moving this way, and this way, but the potential across each one would be exactly the same. So what we need to find out is what is the current through each resistor, what is the potential difference across each resistor, how much power is lost or dissipated across each resistor. Let's calculate this one. So as all the resistors are connected in parallel, the effective resistance or the net resistance is given by this formula here, which is the reciprocal summation. Okay, 1 over R1 plus R2 plus R3. So you have to do the reciprocal summation in parallel combination. So this P here just stands for parallel. So let's plug in all the values. R1 is 20, R2 is 30 and R3 is 40. So if I add them together, what I get is 0.1083. Now, as this is a reciprocal, you have to take the inverse or take the reciprocal, and you will get is 9.23 ohm. The one thing you have to understand is this resistance, the effective resistance, is always smaller than the smallest resistance. What does that mean? Among all these resistors, the 20 ohm is the smallest. The 20 ohm is the smallest. So this one has to be smaller than 20 ohm, which is. So that means it's incorrect. So that's a way of double checking this one. So if your resistor, the effective resistance is not smaller than the smaller resistance, that means you did something wrong. Okay, so this is the effective resistance. So now once we know the effective resistance, what does that mean? That means all these three resistors can be replaced by one single resistor with the value of 9.23 ohm. Now we have a resistor and a potential or a battery or a voltage. Then we should be able to find out the current in the circuit by using the Ohm's law, which is V equals to IR, and I would be V divided by R. So the total current is I equals to V over R, and the V is the 10 volt and R is 9.23. We get 1.08 ampere. So this is the current passing in the circuit. But now as this current is 1.08 is passing here at this junction, it splits into 3 arms. And now we have to find out how much current is now in each arm. So how do we do that? The one way is we know that the potential across all these resistors are exactly equal, and in this case it is exactly equal to 10 volt. So we know this is the 10 volt now. So we know the potential across this one is 10 volt, potential across this one is 10 volt, and potential across R3 is 10 volt. So V1, V2 and V3, the potential is exactly equal to the supplied voltage, which is the 10 volt. So now once I know the voltage across this one and we know the resistance value, then we can find out the current. So all the time I'm using these equation, V equals to IR, and if two are known, then we can find out the third one. So in this case, we know R, we know the potential difference across this one, which is 10 volt. So we can find out I1. So I1 will be equal to V1 over R1. And V1 is 10 and R1 is 20. So it will be 0.5. The same way, I2 will be 0.33 and I3 here is 0.25. And one important point I would like to make here is, so here you see this current is now dividing into three branches. The smaller the resistance is, the more current will be flowing through this one. That would be the preferred path for the electrons. So as this one is the smallest one, the more current will be passing through this one. Let's see. The 21 will have, so this one is 20 ohm. You see this one has more current compared to 40. This one is 40 resistance ohm and this is 20. So double current passes through this one, which makes perfectly sense. Okay. And if I add all these currents together, what you get is 1.08 volt, 8 amp, 1.08, which is exactly the total current in the circuit. So the power supplied by the battery, we're going to calculate the power supplied by the battery. So the power supplied by the battery is given by I times V. And this is I is the current in the circuit and V is the supplied voltage. Current is 1.08 and the supplied voltage is 10. You see this is the supplied voltage is 10 here. So what you get is 10.8 watt is the power supply. So once this power is supplied by the battery, so this power is distributed among all the resistors. Now let's find out how much power is across R1, or how much power is delivered across R1, how much power is delivered across R2. Let's do that. So the power dissipated or power delivered across each resistor is given by this formula here, I square R. And this is in fact the same as IV, where V is equal to IR. This is a comma here. So if I just plug in IV and V equals to IR, we also get this formula 2I square over R. So P1 is I1 square over R1 and I1 is 0.5 square and R1 is 20. So we get 5 watt. And P2 will be now the same way, 3.27 and 2.5 watt. So again, make a note that a smaller resistance in parallel combination, the more power is delivered to the smaller resistance. Higher the power is, a smaller power is delivered. Okay, a smaller resistance will have more power delivered. But if we add all this power together, it will be exactly equal to 10.8 watt, which is in fact equal to the supplied power. So what does that mean? That means all the power that is supplied by the battery is in fact dissipated across the resistor. So there is no storage of the electrical power. There is no storage of electric field. All the power that is supplied by the battery is in fact dissipated. So if you're using a filament bulb or light bulb, all the power is now dissipated in the form of light energy, in the form of heat energy. So no power is being stored there. Like a capacitor can, or in fact it does, store the electrical charges or energy. So let's do exactly the same thing with the simulation. So here I'm using the FATE simulation. So we know that we have 3 resistors. So let's use 3 resistors. And these 3 resistors are connected in parallel. So what I'm going to do, okay, so these are connected in so here I'm just showing you how to connect them. And then we have a battery. So let's take a battery here and then I'm just putting a switch here too. Okay, and now this one was 10 ohm, so it's already 10 ohm. This one was 20, so let's make it 20. This one was, I think, 40 ohm, so let's make it 40. Let me see, I think this one was 20 perhaps. Let me see. So 20, 30 and 40. Okay, so 20, 30 and 40. So this is 20, 20, this one is 30, this is 40. Okay, and this is 10 volt. So this is 10 volt. So now I'm just going to measure a current here. Okay, so let me break this one too. Okay, okay, so here the current, and I can also measure the current into each component too. So let me break here too. So okay, and I'm going to put one more ammeter here and then connect it using a wire. Okay, and then here too, let's have one more ammeter and then connect it. No. Okay, this is the completed circuit, so we should be able to measure the current. So let me turn on the switch now. So you see now, so this is in the parallel combination, and let me the values here too. So 1.08 ampere is the total current, and let's see how much we have got here. The total current we got is 1.08, and each one we get 0.5, 0.33 and 0.25. So let's see here too, 0.5, 0.33 and 0.25, and if I add all this current, it has to equal to 1.08. And now you can also measure the voltage across this one too if you are interested. So if I measure the voltage, how much it has to read, 10 volt. 10 volt. If I measure the voltage across this one, it has to read 10 volt. Okay, so this is using this simulation, you should be able to verify your answer. Okay, if it is a complicated circuit, then you can easily measure the effective resistance, the current into any branches. Again, if you have any questions, let me know. So that this is it from this lecture here. So using the simulation is always helps. It always helps you to visualize the things. This current, and you can see here, let me use the conventional current here, and you can clearly see the current is passing here, and this current is now splitting into 3 branches, 1, 2 and 3 branches, and at this point it again adds up together. So this current and this current now adds up together, and the smaller the resistance is, the more current passes through this one. So this one has 40 ohm, so a smaller current passes. This one has more resistance, so a smaller resistance, more current passes. So this is it from this video. If you have any questions, write down your questions in the comment section below, and do not forget to like, share and subscribe the channel. Thank you very much.